Class, welcome back. This is Michael Knocht. I'm going to be giving a lecture for the first half of the class, about 40 minutes, with plenty of time for Q&A and corrections, and then turn it over to Professor Van Bibber for the latter half. Okay? So this is a continuation of material about nuclear strategy. Next slide. So one of the first important studies that were done in the early nuclear age was the RAND basing study of 1950 to 53. The basic idea was for a group of civilian strategists based at RAND, the Research and Analysis Corporation, that was started by the chair of Douglas Aircraft in the late 40s. And their study was about, is it the right place to base the Strategic Air Command bombers on the coasts? Because that's where they were, intending to get off for the shorter distance to attack the Soviet Union. And this was a study conducted by Albert Wohlstetter, who became a very famous nuclear strategist, Henry Rowan, who became president of the RAND Corporation at the time of the Daniel Ellsberg leaking of the Pentagon Papers, and wound up as a professor at Stanford for many years, and James Digby, who was a close colleague of Wohlstetter and Rowan. They inherited a situation where SAC had based the long-range bombers near the coast for rapid takeoff. But the RAND study demonstrated that Soviet ICBMs could attack and destroy these bombers, and this was the essence of the US retaliatory capability. So Wohlstetter et al. Recommended that the bases be relocated to the Dakotas, to Missouri, and other inland sites. And in general, the whole impact of the study was to emphasize the importance of retaliatory vulnerability as a key issue, and to secure retaliatory forces as a key element of US strategy. This later was released this was a highly classified study, and a summary of it was released in an unclassified paper that Wohlstetter published in Foreign Affairs in the late 1950s called The Delicate Balance of Terror. Next slide. There is the study from 1959, Foreign Affairs. A significant figure in nuclear strategy was Wohlstetter for 40 years. He actually was given the Presidential Medal of Freedom, the highest award to a civilian, late in his career. Brody, who we talked about earlier, became first a supporter, but then a ferocious critic of Wohlstetter, thinking that Wohlstetter was much more concerned about nuclear attack and retaliation than Brody thought was likely. The Delicate Balance of Terror. It's a very famous article, Foreign Affairs. Next. A little bit later in the 1950s, under Eisenhower, another study was done. This was an independent commission called the Gaither Committee.
Professor Knocht, I think we have a question from Michael Santos. Michael, do you want to ask that?
Yes. Okay.
Yes, thank you, Professor. My question was, the study in the first slide was the recommendation based on that they found that coastal-based bombers would be destroyed in an initial attack, and that was the recommendation to move inland?
Right, yes.
Okay, and they could justify the extra flight time to get through the country?
The bombers would have time to get in the air as soon as we picked them up from radar. This is in the early days before space-based reconnaissance.
Okay, thank you very much.
Sure.
And on that note, Professor, can't the ICBMs just go over the pole and isn't it the same distance for the most part to touch the horizontal, I guess, latitude, whether they're on the coast or they're in the middle of the states? Are you expecting direct attack, I guess, laterally?
This was done in the early days of the missile era, when there were very few missiles deployed,
Mm-hmm.
and they thought that they would have to come across the Pacific. Later, you're right, they could come over the pole, and there isn't a huge difference between vulnerability on the coast or vulnerability inland. But that was not true in 1950 to 53 when the Wolstetter study was first done.
Okay, thank you for clarification. Appreciate it.
So the Gaither Committee produced a different study that emphasized the weakness of US nuclear forces relative to those of the Soviet Union. They urged a 50% funding increase in civil defense programs. And they claimed, and this became a big public issue, that there was, quote, a missile gap, unquote, between US and Soviet forces. This was picked up by Senator Kennedy in his run for the presidency in 1960. Although later, after Kennedy became president, they did an internal study and found that there was no missile gap. But this is an important study that influenced thinking for a while in the late 1950s. Okay. Next slide, Mansup. Key figures also that we've discussed already a little bit from the Wizards of Armageddon Kaplan book were Herman Kahn up above and Edward Teller down below. Teller, of course, was a Hungarian refugee, a brilliant nuclear physicist. He was a junior guy at Los Alamos during the Manhattan Project. He was very interested in thermonuclear weapons from the beginning. A rather difficult personality. He did not get along very well with Oppenheimer, who chaired the scientific program of the Manhattan Project. Later on, Teller, after the war, became so convinced of the need for thermonuclear weapons, they advocated the establishment of a second nuclear weapons facility besides Los Alamos, because Los Alamos was not inclined to proceed with thermonuclear weapons development. This is because Oppenheimer was very influential there, and Bradbury, who was also the director of Los Alamos, did not support the thermonuclear program. Teller went to Washington, and after a lot of lobbying, received funding for the building of a second nuclear weapons lab, and that's Lawrence Livermore National Lab. Teller spent many years at Los Alamos, at Lawrence Livermore Lab in Northern California after spending earlier years in New Mexico. Another key issue was the questioning of Oppenheimer's security clearance because of concerns that he had had linkages to the American Communist Party, including his wife, who was a member. And Teller, at a key moment in the congressional hearing about Oppenheimer's clearance, asserted that he did not think Oppenheimer should retain his security clearance. This led to the removal of Oppenheimer's security clearance. And it was a huge cause célèbre, a major national incident. Still further along, Teller became very active in missile defense, in space-based missile defense, and he was a key figure in persuading President Reagan to support funding for the development of a Strategic Defense Initiative, SDI, which was in vernacular called the Star Wars program, which ultimately was proven not to be technically feasible. He passed away in his 90s, Lived his whole balance of his career in Northern California near Lawrence Livermore Lab. Kahn, above him, was trained as a physicist. I think I told you he had gone to the Rand Corporation for a summer internship while a student at UCLA in physics and never left. He became very active in studying nuclear weapons and nuclear strategy. He wrote this massive book called On Thermonuclear War, in which he postulated 8 or 9 different scenarios for nuclear war. He later wrote another book on escalation, which was some of whose ideas were borrowed in Vietnam, US policy in Vietnam. And I think I mentioned to you that I interviewed him for my own dissertation, which was on Vietnam policy in the early 1970s. He had already left Rand and founded his own organization, the Hudson Institute on the Hudson River in upstate New York. And he's the one who said to me, you're pretty smart, you understand about 7% of what I'm saying, which was, I'll translate, you're pretty smart, you understand about 70% of what I'm saying. So he was quite a formidable and extraordinary figure. He passed away of a heart attack in his, I think, early 60s. He's a huge man, about 400 pounds. So these are two of the great wizards of Armageddon, Teller and Kahn. Next. Oh, and he was also a great proponent of civil defense. They were both proponents of civil defense. Another great figure who I got to know very well, a wonderful man, is Bill Kaufman. Kaufman had been at Princeton and Yale, and he wrote one of the first major think pieces called The Requirements for Deterrence. While he was at Yale and Princeton, he then later went to Rand and wound up teaching at MIT, which is where I met him. He emphasized the importance of counterforce capability rather than counter value, attacking the other adversaries' weapons that could attack us rather than the population. And he thought that having a credible counterforce capability was the best way to have an enhanced deterrent capability. One thing that sometimes gets missed by students is the intensity of the competition between the Air Force and the Navy in the early days of the nuclear period. Just because the Air Force had bombers and had SAC and had these delivery vehicles for nuclear attack, it didn't in any way prevent the Navy from wanting to get into the nuclear business. And they had already developed nuclear-powered submarines under the leadership of Admiral Rickover. And then they moved from there to the design and development and deployment of SLBMs, submarine launched ballistic missiles, on SSBNs, on the nuclear-powered submarines. Kaufman was assisted in the early days by two people who also became big stars in this field, Daniel Ellsberg, a major figure not only on Vietnam, which happened later, but also on nuclear strategy, and Andy Marshall. Andy Marshall became the head of net assessment in the early 70s on a temporary assignment from Rand. And he left his wine collection with Jim Digby, thinking he'd be back in a year, and he stayed 45 years. He retired just a few years ago and passed away. He was about 95. And these were all people and ideas who McNamara was closely associated with, closely involved with, and they wrestled with these ideas at great length in the 60s in particular, but even more so even beyond. Any question about Kaufman? Oh, Kaufman also had the distinction of writing the defense posture or white paper of every Secretary of Defense from McNamara in 1961 to Harold Brown in 19 79, 1980. So 20 years, he was the principal author of the posture of the United States across all linkages. He didn't write every part of it, he collected it, but he was a brilliantly lucid writer. And he was the primary author of all of those, irrespective of party, from the early 60s to the late 70s. When Reagan came in, he didn't want to use Kaufman anymore. Okay, next. So another dimension of nuclear strategy had to do with extended deterrence. That's in red, to protect US NATO allies from attack. We were not only concerned about an attack on the continental United States, but an attack on Europe and on our NATO allies, the French, the Germans, the Italians, the British, of course, and others. And the term that was developed was extended deterrence. And this was an effort to develop weapons that could be used to deter or defeat a Soviet attack on our NATO allies. One of the big differences that developed at that time was, and this also involved counter-force targeting. One of the issues that developed at that time was the difference that we developed with the French. The French detonated the nuclear device for the first time in 1960, and they developed their own capability, which was not integrated into NATO planning.
Professor Knock?
Yes?
Andrew Morello has asked a really good question.
Yes?
Andrew, can you ask that?
Sure. I was curious to know, sorry, and I need to go back and read my own question here. Why, do you know or have any inclination to why Oppie and Lanel did not support thermonuclear weapon development early on? Was it based on a kind of ethical dilemma for Oppie and for Lanel, or was it something else?
It was in part based on the fact that Oppenheimer was so moved by the enormity of the destructive power of fission weapons that he really didn't want to be part of any further development to enhance their capability. He thought the fission weapon was highly destructive and nothing beyond that was necessary. And as long as the US felt that the Soviets were not involved in thermonuclear development, he didn't see any reason why the US should enter into that. Okay?
Thank you.
Now it's mentioned in the first dot under the Kaufman dot in the slide, the father figure of the French nuclear program was General Gallois, General Pierre Gallois. He was a general in the French army, but he was really a great nuclear strategist for the French. But he was a tremendous supporter of city busting, of counter-value attacks rather than counter-force attacks. And a brief anecdote, I had a chance in the late 1970s on a trip to Europe to visit General Gallois. He wasn't available for a meeting in his office, but he invited me to his home for dinner. He had a beautiful home, an apartment in the 16th arrondissement. The 16th arrondissement is like Pacific Heights. It's the most beautiful section of Paris. And when I went there, because I'd never met him or anybody else before, he introduced his wife and to myself, and he said, just the three of us will have dinner, General Gallois, Madame Gallois, and Professor Knock. And we sat at a very, very long table. General Gallois was at one end, Madame Gallois was at the other end, and I was in the middle. And there were various servants serving a very elegant dinner. When the dinner ended, General Gallois motioned to his wife, like with the back of his hand, to sort of say, you're dismissed. And she left the room. And he said to me, he spoke good English, he said, we will go into the study for brandy and cigars. this is all brand new to me. We went into a study, beautiful book-lined study, and we sat down in these comfortable chairs. And he said to me, "You may wonder what is the motivation behind the French nuclear force." And I said, "Of course, I'd love to hear your thoughts on it." And he said something to the effect of the following. He said, "Monsieur Nacht," he said, "we French have fought many wars since 1870. In 1870, we lost to the Germans. In 1914, World War I, we lost to the Germans. In 1940, World War II, we lost to the Germans. In 1954, in French Indochina, we lost to the Vietnamese. In 1958, 59, we lost to the Algerians. You see, every war that we fought, we've lost. We cannot defeat countries with conventional forces. That's why we need nuclear weapons to protect sovereign French territory from our adversaries." And he said it with such force, such emotion. It was an extraordinary moment. I mean, he was a great French patriot. He felt deeply that nuclear weapons was the only security for the French. So I thought I'd share that little anecdote with you. There at the last dot, I mentioned what I said before. Kaufman, chief author of the Secretary of Defense Posture Review from 61 under McNamara to 80 under Harold Brown. There's McNamara in the upper right-hand corner with a map of Vietnam. And the lower right is Harold Brown. Harold Brown was a brilliant physicist, got his bachelor's in physics from Columbia at 19, and his PhD from Columbia, I think at 21 or 22. He went out to work at the newly established Lawrence Livermore National Laboratory and very quickly became the director of the laboratory. And later on, he was US Secretary of the Air Force. And then under Jimmy Carter, he was the Secretary of Defense. He just passed away in his early 90s, within the last year or so. A gentleman, quiet, reserved, extremely smart. Okay, continuing on the evolution of US nuclear strategy through the personalities, we move on. Just a little further here, a little bit more repetition. Kaufman was personally skeptical of the utility of civil defense programs. Kahn was much more supportive. Kahn was also the model for the Dr. Strangelove film. How many of you, show your hands to our colleagues, how many of you have seen the film or heard of the film Dr. Strangelove? Mansuk, how many?
I think about 10 plus,
About
about
half
15.
About half the students, okay.
Right.
I highly recommend that you see this film. It is an extraordinary film. It's sort of a mockery of nuclear strategy and strategists. Probably modeling in a way, partially the behavior of Kahn, who was viewed sort of like as a mad scientist. There's Kahn up above in the right-hand photo with his thumb in the air. Down below is Peter Sellers, the gifted British actor and comedian. He played 3 or 4 different roles in this movie, including the role of Dr. Strangelove, who also had pro-Nazi sympathies in this film. After the film came out, it was highly controversial. James R. Newman, who later compiled a fantastic 4-volume set called The World of Mathematics. James R. Newman wrote about Dr. Strangelove. This is a moral tract on mass murder, how to plan it, how to commit it, how to get away with it, and how to justify it. So Newman was not a fan of Dr. Strangelove. but it had a lot of impact on people's beginning to understand the people who are actually thinking about nuclear weapon use. Always a small number in the United States. Next. How are we doing on time here? We only have about, we have a little time, about 15 minutes. The issue also came about how do we develop our nuclear war plans? And these were ultimately developed into something called the SIOP, the Single Integrated Operational Plan. They were figured prominently in the Cuban Missile Crisis of 1962. There had been an earlier crisis with the United States and the Soviet Union over Berlin. When Berlin was physically in Eastern Germany, but it itself was divided into four parts, four sectors, a British, a French, an American, and a Soviet sector. So East Berlin's West Berlin was very vulnerable because it was completely surrounded by East Germany. And I'll skip over what happened in that Berlin crisis of 1961. There was always a feeling the US wanted to push the United States out of Berlin and out of Germany. But in 1962 was the famous Cuban Missile Crisis. I'll just very briefly summarize a couple of the key points. Under Khrushchev, the Soviets sent nuclear-tipped missiles on ships to Cuba, which was a communist ally of the Soviet Union after the Castro regime took power. This was viewed with great concern in Washington. This was under the Kennedy administration, for fear that the Soviets could launch nuclear missiles from Cuba against the United States, or could threaten to launch them and intimidate the United States.
Professor Knock, I think we have a question from Anthony Dye.
Yes, please.
Hi, Professor. And my question is, like, at the time, I think like Soviet had a sort of a like strategy or tactics called sausage tactic. Basically means that it's like a hypothetical like strategy that at each of the stage, they will not actually triggering something that very overwhelming to actually triggering the nuclear counterattack. And it's a major threat to the like Western Europe. Does U.S. at the time have a certain like nuclear strategy to countering that kind of slowly infiltrations and slowly like relatively like slowly like devouring attack?
If I understand what you said, I don't think there was anything really comparable in the United States. The US was basically going through fits and starts incrementally to the development of a counterforce capability as a credible retaliation against the first strike. This was our main concern. And we began to deploy tactical nuclear weapons in Europe to defend against the Red Army attacking Western Europe. Those are the key elements of US strategy, not a kind of sausage approach, which implies limited use of nuclear weapons at limited times. Okay?
Thanks.
Just to finish up on the missile crisis, another little anecdote here. There was great concern about the deployment of these weapons. It, of course, was top secret originally until Kennedy went on national television on a Monday night to announce to the nation that our aircraft, our U-2 aircraft, which were intelligence gathering aircraft, had discovered these missiles that were deployed, that were ready to go on Cuban soil that had come off these ships from the Soviet Union. And Kennedy both insisted that these missiles be removed and that no further shipment of missiles be sent by ship. A personal anecdote, I was in college at the time, and I was in an engineering class in electrical engineering. I remember circuits class, I still remember it very vividly. And Kennedy spoke on a Monday night, and I went to class on Tuesday. And the professor said that he had planned to give an exam, midterm exam on Thursday, but he decided not to do it. And this was a chilling comment because he didn't think he'd be alive to grade the exam. Did not think he would be alive to grade the exam. This gives you an idea of just how serious the concern was about a nuclear exchange with the Soviet Union at that time. Well, I'm still here, and we're all still here because there never was an attack. Instead, Kennedy had this two-pronged approach. First, he said in his speech that any attack by any of these weapons against anywhere in the Western Hemisphere would mean a US counterattack against the Soviet Union. So it was direct threat of nuclear deterrence, nuclear retaliation. Secondly, he ordered a quarantine, a naval blockade. After all, the U.S. had great asymmetric advantage with U.S. ships in the Caribbean, very far from Soviet soil, and a blockade to prevent any of these ships from coming into Cuba. And there was at one key moment, it looked like there was going to be a confrontation between Soviet and American ships, but the Soviets turned back. They did not confront the United States. So at the end, the crisis was averted. What we didn't know at the time was that the US agreed secretly to withdraw some theater nuclear weapons from Turkey that were kind of obsolescing. These were Thor Jupiter missiles that carried nuclear weapons from a NATO Turkish base to the Soviet Union. We agreed to get rid of those weapons. And Kennedy also pledged not to try to overthrow Castro, which we had already tried twice to do and failed. These two pledges by Kennedy were not published at the time until later. But Kennedy was given great marks for averting the crisis, getting the missiles out of Cuba, and basically prevailing. And Khrushchev was very much vilified in the Soviet Union for that, and it probably led to his loss of his position. The Cuban Missile Crisis was in October 62, and 2 years later, Khrushchev was ousted in October 64 by Brezhnev, who then was the General Secretary of the Communist Party for over 15 years. And again, McNamara's view on strategy was damage limitation. You wanted to be able to have offensive capability that would limit the damage to the adversary, but do enough damage to prevent them from feeling that they could launch an initial strike. So in the photo on the upper right is a meeting of the XCOM, which was a special executive committee formed by Kennedy to review policy in the Cuban Missile Crisis. You can see if you look carefully, there's Kennedy sort of straight ahead on the other side of the table near the window. There's Mac Bundy, there is the National Security Advisor, there's McNamara on the left side, Dean Rusk, the Secretary of State. This was a high watermark of tension in the US-Soviet Cold War. And down below, there's Kennedy, Castro, and Khrushchev. One of the definitive books on the Cuban Missile Crisis is called Essence of Decision by Graham Allison from Harvard. It's a wonderful book about all the decisions involved in the Cuban Missile Crisis. Highly recommended. It's one of the most widely sold books by political scientists in the United States. Okay, how are we doing? Do we have a lot more, Mensuk, or?
One more slide.
Okay, so just finish up here. Kennedy's science advisor was Jerome Wiesner, an MIT physicist who then later became president of MIT. And he and Kennedy were close till Kennedy was assassinated. There's this famous picture of Mrs. Kennedy climbing over in the car to protect her husband after he'd been shot in the head in the Dallas assassination of Kennedy. That's him to the right just before it happened. And there, later on, after Kennedy, there was Johnson, and Johnson got all involved in Vietnam. The key battle was the Battle of Quai Son, where American Marines were encircled in a huge battle where the U.S. considered use of nuclear weapons against the Vietnamese, but Johnson chose not to use them. There was also at this time the triggering of the ABM debate about missile defense, which I discussed earlier, and whether it's destabilizing or not. This is all taking place in the 1960s under Kennedy and Johnson. Next, that's it, okay. I should just say one final anecdote. I was just starting my career, and I was a NASA space science aerodynamicist at a research lab in Ohio. And I used to run wind tunnel tests. And the wind tunnel required tremendous electric power generation. So the tests were only done at night when the city of Cleveland had their lights out. So I had done a test on the evening of November 21st and was sleeping during the daytime on November 22nd, the day Kennedy was killed. And I was living in a small apartment by myself, but I had a fiance back in New York. And out of the blue, the phone rang, and she woke me up to say it was my fiance, to say that President Kennedy had been shot and killed, which was just so startling. It was just staggering. And I quickly got dressed and went to the lab. And for the first time in my life, I was very young, in my early 20s. The guard, I had my badge, but the guard told me to get out of the car. I did a complete body search on me, touched every part of my body, making sure that there was nothing sinister that I was up to. And I went then into the lab through security and went to my group, and everyone was watching the television. And there was television coverage of the Kennedy assassination right through the weekend, which included the arrest of Lee Harvey Oswald as the killer, and then his assassination by Jack Ruby. I don't know if you're familiar with any of these names, you may not be. And actually, even on Monday after the assassination, Kennedy was killed on a Friday. So I was at home all weekend, glued to the television, watching the developments. And then on Monday was his funeral. It's an extraordinarily emotional, difficult time. So I've lived through these periods, and it was not fun. Okay, I think I've gone over, and I turn it over to Professor Ben Bibber and Minso.
Thank you, Professor Na.
Great.
Professor Bieber, you can share your slides.
Great, thank you. Let me do that. I'm still fumbling here. Let me fumble for a minute or two more. There we are. I'm going to share. Okay. Actually, let me thank Julia Whitworth from Los Alamos, who actually put in the chat a recommendation on the book 13 Days. Let me add one of my own. Although you've got plenty of reading here, so nothing I recommend to you is required. They're just simply, if you really are very much into these histories, these are things that you should read, or sometime later when you have the time to do these readings. It turns out that everyone thinks that Nixon was the first person to bug his own Oval Office. It turns out that's not true. It turns out that Kennedy himself had microphones underneath the table in the room there, and for the entirety of his presidency. And it turns out into all the conversations that happened there, that in that photograph that Michael showed you, Professor Knox showed you, during the entirety of the Cuban Missile Crisis were there. And Ernest May and Philip Zelikoff actually have taken those tapes and transcribed them. And sometimes they will put a little parenthesis saying, the voice is indistinct. We don't know who the speaker is. This is garbled. We think this is what was said. This came out, 20 some odd years ago. It is absolutely fascinating because it actually shows almost a kaleidoscopic thinking about, coming from complete shock, the discovery in these overflights of missiles in Cuba, to saying, getting to the bottom of it technically, and then saying, why is this happening? What are they really after? Developing what they called a mental crutch, i.e., this is a replay of the Suez crisis, or this is all about Berlin. And then Kennedy is sitting back for several days. The first 5 or 6 days, he's kind of in information taking mode. And it's not clear where he's going to come down on these things, or that he's actually formulating any plan of action. And then about day 6 in, Kennedy, all of a sudden you see he's got everything he needs. He's now formulated a clear enough picture. He's all of a sudden sort of dominating the conversation. They're moving forward, and then at the end of 13 days, they come to this very successful resolution of it, and where we took out the old missiles from Turkey, which apparently were obsolete anyway. We were going to get rid of them, and then the thing ultimately came to an end. And it turned out, in the end, after they had opened up the 1992 the files of the KGB, it turns out, in fact, indeed, behind this was really Berlin. Really quite fascinating. I recommend you do read that. Another book that I provided some help to Bruce Charter with, who had actually hired me at the lab many years ago, the American Lab, which was a story, many things have been written about Los Alamos. This is the book on Livermore, where he kind of turns the conventional history or the conventional wisdom on its head, although Teller is in a certain sense kind of the guiding spirit or the figurehead of it. This was really Ernest Lawrence's dream, and it was really built with very new and very green people who had no history in the nuclear weapons business, but had to learn fast on the fly. As opposed to many people of these very distinguished scientists who were, emigres during the Nazi oppression in the 1930s, who went and joined the American project, the Manhattan Project in Los Alamos. I play a very tiny role in the book there that you'll actually find if you read the book on one project I was involved with there. Professor Knox said those were harrowing times. I remember, in the how traumatizing the whole thing, the Cuban Missile Crisis was, thinking there was just no place you could run, nowhere you could go. You could be incinerated literally in 30 minutes. I grew up in Connecticut, halfway between Boston and New York, and there was nowhere to hide. It was going to come down on us. Okay, let me do as we always do. Can everyone? Is the screen shared yet or not yet?
The screen is shared.
It is.
You need to expand it.
Okay, there we are.
There you go.
Okay.
Everything's good.
Good. Great. As always, what I do is a brief reprise of the last lecture, simply to consolidate and reinforce the key ideas. Let me just leave you with a half a dozen things which are important for you to remember about fission, and then we'll move on to nuclear reactions. It's a process by which a very heavy nucleus, the things of concern to us are in the actinide range, mass 230 to mass 240, violently splits apart into two fragments with a very large release of energy and neutrons. It all works because the binding energy per nucleon for an actinide is about an MeV per nucleon less than it is if I were to divide the nucleus into two medium weight fragments. That's where you get the number roughly of 200. It's mostly the energy is mostly released in the fission fragments, recoiling fission fragments, which of course are going to deposit that energy thermally in the material that it's in. But you do get out between 2 and 3 neutrons. It's a distribution, but on the average, depending on what the species is and at what energy, what excitation energy the nucleus fissions at, it's typically between 2 and 3 neutrons, which is enough, even including loss of neutrons downstream, to give you an exponential multiplication. And you get out some gamma rays, a few MeV of beta particles, and totaling up to 100. The other thing is, of course, since the chart of the nuclides bends over, that these very heavy nuclei are neutron rich, when you split the nucleus in two, what you're going to end up with are fragments which are almost invariably very neutron rich, and then we'll have to subsequently beta decay down back to the valley of stability. And that what gives rise to these very, very problematic species, which can lead to very, very, very long-term contamination and of course, delayed health and environmental effects after an above ground test or use. Not terribly important, but just to know is that, of course, the fission is an asymmetric process. Typically, you have something around mass 90 and something around mass 140 there, with a symmetric split being very, very disfavored. Okay, one additional thing here I forgot, and I had realized I just omitted to say this until Jake, who's preparing the first homework, was using a unit in the homework, and I said, oh my gosh, I forgot to define a couple of things that you will find useful. Two equivalent units for the number of decays or disintegrations per second of an unstable species. One which is less used now, in fact disfavored, is the Curie, which is 3.7 times 10 to the 10th decays per second. And you might say, well, where did that number come from? In fact, it simply was, when it was a formal definition, was rounded up from what's called the specific activity of radium-226, an isotope that the Curies spent a great deal of time in the early career studying the properties of radium, and which is 3.66 times 10 to the 10th becquerels per gram. Specific activity is disintegrations or decays per second per gram. Now, I've now talked about a becquerel. Becquerel is much simpler. It's simply, a becquerel is simply 1 decay per second. Nowadays, most people will express things in becquerels rather than curies, but you will hear both. Just to do an exercise, although I don't have a chalkboard, I did something on my iPad and then just scrolled it up. Let's actually go ahead and calculate, okay, if that's, can we actually go back and actually derive what the Curie is, 3.66 or 3.7 10 to the 10th decays per second from the specific activity of radium. Well, so let's do that, because I think it's good to just limber up and become familiar with your Brookhaven National Nuclear Data table there. So first thing you do is to say, well, okay, how many moles in a gram of radium? As you know, the atomic weight of something is defined to be the mass in grams of a mole. Okay, so if I have 1 gram, what's radium? Well, it's a tad over 226. For all practical purposes, you could call it 226. So the number of moles is 1 over 226. How many atoms does that represent? Well, a mole is 6.02 10 to the 23rd. You multiply them and you get 2.6, 2.7 10 to the 21. Okay, then you say, what is the half-life? Well, now you need to go to the nuclear data, have fun with this interactive table. So you go to the Brookhaven table, you put the cursor until it lands on radium-226, you zoom in, and you actually see this little table down here, and you see it has a half-life of 1,600 years. Now I've written it as A. If you want to be part of the in crowd, I think in scientific literature nowadays, a year is an annum. So a GA is a giga-annum. So if you want to be hip, you don't write YR, you write A. 1,600 years. In seconds, that's 365, and then 86,400 seconds a day. So it's 5.05 10 to the 10th seconds is the half-life of radium-226. Okay, what's the decay rate? If the mean life, the decay rate is 1 over the mean life, but the relationship between a mean life and the half-life is a natural log 2, so it's 0.693 over 5.05 10 to the 10th, 1.37 10 to the minus 11. And therefore, a Curie is multiply the number of atoms times the very small probability that any one of them will decay in a second. It's a very tiny probability, but when you got a lot of atoms, you're going to have a lot. And it turns out to be 3.7 10 to the 10th per second. So that's where Curie comes from, starting from the definition of a specific activity. Okay, so let me close this out and we'll go on to our next topic, which is here, nuclear reactions. So let's go to the nuclear reactions. And we're now going to start looking at processes where you have at least, you have 2 bodies in general in the entrance, in the what's called the entrance channel or the initial state, and 2 or more species in the sometimes 1, but usually 2 in the final state. Classic case of great relevance to this course is a deuteron plus a triton going to a helium-4 nucleus plus a neutron like this. You've sort of gotten the drift of this thing now. You remember, playing around with the chart of the nuclides, that helium-4 is an exceptionally well-bound nucleus, very tightly bound. Therefore, when I go ahead and calculate the Q value, then since it being much more tightly bound, the sum of these, it's a smaller mass, and therefore the difference in masses, either working through AMUs or mass excesses, however you want to express the masses, is going to give you a lot of energy. When you go ahead and calculate the Q value, and we've done this before, you can do it again, it turns out to be close to 18 MeV, or about 3.5 MeV per nucleon. This should, you should look at this and say, gee, this looks tantalizing as an energy source. Fission, about 200 MeV energy release for something weighing about mass 240. So it's about 0.8 MeV per AMU, atomic mass unit. This looks better. Why aren't we doing this thing? Okay, that's a good question. We'll come to this in just a moment. Okay, all right, so that's a nuclear reaction. What other types of reactions do we have in general? Well, let's just stick for the moment to two-body reactions. There are some very important astrophysical reactions that are actually three-body reactions in the early universe and in astrophysics. Let's not talk about those. Those are very uncommon in usual circumstances, but nuclear reactions in general are a two-body. And very often two-body to two-body. So it's A plus B going to C plus D. I didn't write these in any particular order, but the simplest one here in line 4 here is what's called elastic scattering. So I have two particles come in, they go out in the center of mass frame at some different angle, but there is no loss of energy and no change in the identity of the species. So protons scattering off of carbon-12 ground state, going to a proton plus the carbon-12 ground state. What's the next most complicated thing that can happen? Well, I can have a proton coming in, interact with the carbon, and the carbon will be excited to its next highest, to the second, or to its first excited state, the second quantum state there, which is at 4.43 MeV. Being a relatively simple nucleus, the spacing in general, for the lighter nuclei, the spacing of the levels is larger. So I can come in this with the center of mass energy of a certain amount, scatter, and now they come, the proton and the carbon recede from one another, but there's 4.43 MeV energy less in kinetic energy, but 4.43 MeV has actually been turned into the internal energy of carbon. I can then have lots of other things. I can have charged particle reactions. I can have a proton and a carbon coming in, a neutron coming out, and nitrogen 12 being left behind. I can have, we talked about a charged particle reaction here, deuteron on a triton giving rise to helium-4 plus a neutron coming out. Very important class of reactions are what are called neutron capture gamma reactions. These are neutrons coming in, which goes to the next heavier isotope of that target, in this case carbon-13, with the energy now being released in the form, the carbon-13 decays down to one or more gamma rays. Here I've just drawn one gamma ray, and then coming out, and then a high energy gamma ray. Since typically the neutron separation energy of nucleus, how much energy does it take to take a ground state nucleus and pull a neutron out? You can just, again, go to your N to C table and take any particular nucleus near the valley of stability, and now look at that mass compared to the isotope, which is one neutron lighter and a neutron, and you'll actually find the cost of that is typically 6, 7, 8 MeV, something like that. If I time reverse that process, if I have a neutron coming in, a very, very slow neutron coming in, then, and if it decays by a single, if it gets rid of that energy by a single gamma ray, the gamma ray going out will be that 6, 7, 8 MeV, something like that. Gamma rays themselves can induce nuclear reactions, and a very important reaction, both in cosmology, astrophysics, Other, let's say, applications is actually photodisintegration. So gamma rays can smack a nucleus and disintegrate it. In the case of hydrogen-2, the photon can be absorbed, and then on the final state, you get a proton and a neutron. All of these things are possible. Now, there's a few rules of the road. 3 things in particular. You have to conserve energy. That's the kinetic energy plus the internal energy, what's called the excitation energy of the species. Total nucleon number has to be conserved. That means the sum of the protons and the sum of the neutrons. As you know, as you've seen, beta decay it violates simply the total sum of protons and neutrons, simply because a neutron can convert into a proton, a bare neutron can beta decay into a neutron, or an atomic nucleus, you can have, if it's away from the value of stability, you can have a neutron turning into a proton with the beta particle and the antineutrino, or the converse process for something which is proton rich there. But the total number of nucleons, proton plus neutrons, is strictly conserved. And lastly, of course, is charge. Charge has to be conserved. Okay. Now, here's an interesting question. If you actually look at the history, and you have, and I showed this when we talked about this tremendous gaffe of Lord Rutherford, who said, nonsense, never get energy out of nuclear physics. And literally 3 years after he died, we had, 2 years after he died, you have the discovery of fission, and you had a reactor 4 years later, an atomic bomb 7 years later, and power on the grid 13 years after the discovery of fission. 1954, you had nuclear submarines. And today, 17% of the electricity in the world is by fission reactors. So it's what I call falling off a log. Can't miss. It was, it's technology, but there seems to be no difficulty here. Fusion. You say, gee, look at this. You've got 5 times greater energy release per nucleon, very light species involved. The UK patented this. There's this famous patent, the Thompson Blackman patent in 1946. Eisenhower declared Project Sherwood. We're going to have this crash program to develop fusion energy in 1955, originally classified. The labs were involved. Princeton and New York University, interestingly, was the original team in Project Sherwood. And now we're in a situation where, break even might be like 10 years from now or so. Power on the grid about when I'm 100 or so. Like what happened? What's a simple question? What's a simple answer? So somebody pop in and tell me, why was this very simple reaction so difficult? And the first one, like falling off a log. Anybody?
The conditions to make it happen are very difficult to reach.
Yes, but why?
You need high temperature and high pressure, and you need that confined for a large amount of time.
Yeah, but why?
You have to overcome the Coulomb interaction between your atoms. That's
it. The case of the neutron, there's no Coulomb repulsion between the neutron and the target, the uranium. Just any neutron coming in, it's going to come in, be captured, and give rise to fission. In the case of even very light nuclei, charge 1 against charge 1, like this, it takes the Coulomb barrier is, I don't have it on the tip of my tongue, but it's, several hundred kilovolts of energy to get them close enough such that the 2 nuclei touch. And as Josh has talked about, and just implicitly, high temperatures and high pressures to get enough of them of enough energy such that occasionally they're close enough to fuse. In fact, in the R&D machines, the tokamaks today, which give rise to fusion, or the laser fusion facilities like NIF at Livermore and so forth, rarely do these nuclei actually pick up enough energy to actually touch one another. They in fact have not gotten to the classical touching radius of like being a Fermi apart. You're still counting on quantum mechanics helping you out by a process called tunneling. You can actually quantum mechanically penetrate a potential barrier, which classically would be forbidden. So exactly right, that's the problem. Now, I put down here the 2032. I think if any of you are young and idealistic and want to change the world, let me put in a plug. Why don't you go to MIT and work with Dennis White on the Spark project? That could be the hottest thing going right now. It's a fusion concept. It's a fusion machine built with high TC superconductors. Instead of ITER being at 10 Tesla, this would be a 20 Tesla machine. All the goodness of tokamaks go like beta, the magnetic field to the 4th power. The claim is that they are able to make a much more compact machine that could be producing, a few hundred megawatts thermal in 5 to 10 years. Now, that's again, we've had many disappointments and delays and so forth in the fusion business. So the real life will probably be a little more complicated than that. But I think it's a really interesting new concept. It's already attracted a lot of money, and he's got a lot of momentum with the with his team there now. Okay, general notation. You can write it out, A plus B going to C plus D. Typically in nuclear physics, we write it in the following way. We write a parenthesis. The beam is in the parenthesis to the left of the comma, and the ejectile, or the observed particle to the right, and then the target to the left and the residual to the right. This is a typical way of writing a reaction. Okay, now, I want to introduce a concept here, and let me be a little bit pedantic because you may not have gotten to this yet in those of you taking Lee Bernstein's class. But just let me give you a sense of how nuclear physicists measure an important quantity which is called the cross section, which is the quantity which contains the essential physics on how readily does a reaction go or not go. Okay, so here's the mental image. Imagine that I've hidden bowling balls inside an enormous bale of hay. So think of this as like little, I don't know, raisins or cranberries in some kind of baked bread or something. You can't see them, but they're in there. And the question is, how could you possibly measure these things without going in there and then measuring them with a yardstick? And then obviously for very tiny things, you're not going to be able to do that. So here's how we go about it. The density of the bowling balls, let me just tell you, is n, small n, and that will be the number per cubic meter. So how would you go about this? The way we proceed in nuclear physics is that we take a shotgun and we are now going to blast away at the bale of hay. Now, you can know in advance to say how many pellets are going to fly out of the barrel of the gun. You might have even loaded your own ammunition. You might say, well, we've got 100 little lead pellets here. And what you're going to do in the most primitive measurement is actually say how many actually came out the back end of the bale of hay. If there's no hard objects on the inside, then just penetrating through a bale of hay, they'll all come out the back side. If I measure a certain number coming in and a lesser number coming out, I have learned something about how many have been scattered at some wide angle and taken out of the beam that's going forward at 0 degrees. So I have a bale of hay of thickness T. And the definition of the cross-section is the following. This is a total, what's called a total cross-section. The number of scattered is going to be the number shot in times the areal density. So the number per cubic centimeter times the thickness will give me the projected density. In other words, if I had X-ray vision and could see the bowling balls, I would actually see a certain number of bowling balls per square meter or per square centimeter, whatever you want. If you're dealing with bowling balls, probably per square meter is more convenient, like that. And in the regime where the target is thin enough that you don't get shadowing of one bowling ball by another, but they would all be, if I were actually able to see all the bowling balls, you would see all of them unoccluded, then the definition of the cross-section would be the number of scattered ones divided by the number in the beam divided by this areal density. And when you think about it, it stands to reason. It's simply giving you think of it geometrically, the cross-section times this areal density is the fraction per square meter which is occluded, and therefore the fraction, if the pellets come in and very uniformly like this, which are not going to make it out the back end. Okay, most primitive way of thinking about the cross-section. Going back to the early days, and I can think probably to the 30s, the definition of a cross-section was a barn, okay, and it was defined to be 10 to the minus 24 square centimeter. Now, why was that a convenient measure? Let's see if anybody can take a guess based on everything we've heard in the class up to this point.
Would that be the units of an angstrom squared?
Well, an angstrom is the size of an atom.
Not an angstrom.
Yeah. 10 to the minus 8, that would be 10 to the minus 16 square centimeter. The idea is that when you look at a proton, it's got a radius of about a Fermi, which is 10 to the minus 13 centimeters. A real heavy nucleus being 5 Fermis in diameter or something, would have something on the order of 10 to the minus 24 square centimeter in terms of its geometrical cross-section. This has a certain appeal because we've said that the nuclear force is a short force, and therefore one might say if I shoot a proton past an atomic nucleus, there won't be a scattering event or a capture event unless somehow you're within this quote unquote geometrical area of the nucleus. Now, watch out, because this notion turns out to be treacherous, but okay. Was there a question? Okay.
No, I was just going to say, I think it has something to do with the joke, couldn't hit the broadside of a barn.
It may have that too. Yes, because there's lots of other objects that you could have named it after, but yeah, it could very well be, because that goes back to pre-war days. Now, this is interesting. So here's a log scale. Here's a graph, bar graph, with the capture cross-section. So of a neutron coming in and capturing on the nucleus. And you see 3 colors there. I'm abysmally colorblind, but I believe they're blue, red, and yellow. Look at the yellow bars there, and I'm looking at Neptunium-237, Curium-246, I'm looking at Americium-243. I'm seeing a whole bunch of actinides there. The yellow bars are indeed all of the order of a barn. So yeah, as you know, actinide nuclei have 6 or 7 Fermi radius, pi r squared. So in fact, that is a number which comes out to be on the order of 10 to the minus 24 square centimeters. if I slow down the nucleus to thermal energies, or what's called well thermalized, energies, all of a sudden I'm finding numbers which are 10, 100, 1,000 times larger. And you say, well, what's up with that? We don't want to get into that right now. This is getting into the deeper secrets of quantum mechanics and nuclear physics, resonances, and so forth, which you're going to learn about in Lee Bernstein's course. We're not here to learn, nuclear physics, but simply to actually just understand these things and to utilize them. Here's a table, by the way, of selected thermal neutron absorption cross sections. And you see for neutrons on helium-4, it's basically 0. And then you have some very odd fish like xenon-135. Cadmium is another thing with an enormous capture cross-section. I think it's about 800,000 barns, which is 2.6 million barns. You say, what's up with that? Okay, it is what it is. So when neutrons become slow, there's a much higher probability that they will be captured, in fact, larger than what you call the geometric, quote unquote, geometric cross-section. Cadmium, I just talked about, has a very, very large capture cross-section. And I want to show you, this is a really good YouTube, it's about 5 minutes or something like that. So let's watch this and we'll hang it up for today. But this is a really interesting pedagogical talk.
These pieces of plastic surround a slow neutron detector that consists of helium-3 gas in a proportional tube. And this electronics over here is counting the response of that tube to neutrons. Here we see the meter is showing about 50 neutrons per second, or about halfway up the scale. As I've noted the previous video, the neutron source in use here is a fast neutron source comprised of americium in close contact with beryllium, and it releases neutrons with a mean energy of about 4 MeV. In contrast to that, the detector tube mostly detects slow neutrons that have been moderated in the plastic and reflected back into the tube. Now we're going to place a piece of cadmium, which is a very strong absorber of slow neutrons, around the proportional counter, and we will see how that impacts the count rate. So first I'll take this piece of plastic out, and then I will temporarily remove the fast neutron source, if the tape will allow me. And we'll place the cadmium sleeve onto the tube. And I will replace the neutron source and the piece of plastic. Now let's take a look at our count rate. It's taken a serious hit from the cadmium attenuation. It used to be up there at halfway up the scale at 50 per second. Now it's barely at 10 per second. So more than 3/4 of our neutron flux, our low energy neutron flux that had been making it into the tube, is now being eaten up by the cadmium. Let's try a somewhat different experiment. I'm going to take the cadmium sleeve off the tube. And in this experiment, I'm going to place the neutron source into a cadmium sleeve, like that. Now I'll place the cadmium covered source onto the tube. And I'll replace the piece of plastic. And we will see what this has done to our neutron count rate. We used to be halfway up the scale, almost 50 counts per second before beginning this experiment. Now we're almost at 40 counts per second, or almost only 1/5 of where we were when we had no cadmium whatsoever in here. So in contrast to the previous experiment where the cadmium sleeve covered the tube and attenuated 4/5 of our neutron flux getting into the tube, now we are putting the cadmium around the fast neutron source, and the neutrons at the high energies have no trouble getting through the cadmium. They're being moderated and reflected back into the detector by the surrounding plastic.
Good. I think I want you to think about that. And what we will do is next time we're going to pick up, I think Monday we have a federal holiday, but on Wednesday we will split the lecture again. And I want you to think about that experiment, and then we're actually going to finish up our short little piece on reactions here. And I'm going to actually show you some what are called excitation functions, some cross sections as a function of energy, to show you some very important phenomenology, very important systematics that are going to be quite relevant to the whole business of nuclear energy and nuclear weapons. Any questions before we knock off for the day?
I
Okay.
think Jake has a good one.
It's rather funny that you should pick that video. That was Carl Willis, who was our guest lecturer last week in NE 290, and who's a dear friend of mine.
Where did you know him from?
I've known him for almost a decade now. We met through fuser.net, which was a website for amateur nuclear science.
You were one of those. You built a fuser in high school. I should have known.
Of course.
Of course. That's our Jake. Okay. Great. Now he actually has a whole series of those things. He's located where?
He is currently in Albuquerque, but he is a lecturer at the University of New Mexico.
Wonderful.
The reactor.
Great. Thank you all. Have a great holiday, and we'll see you on Wednesday.
We'll see you in discussion on Friday as well.
Thank you.
Thank you.